Hello and welcome to the Unit 7 Section 2 video on interior and exterior angles of polygons. So in the last section we talked a little bit about how to identify polygons, how do we classify them as regular or irregular, convex or concave. Now we're going to take a little bit closer look at the angles themselves and what we can do with those. So to find the sum of the interior angle measures of a convex polygon, you draw all the possible diagonals from one vertex of the polygon. This creates a set of triangles. So for a triangle, there are no diagonals to draw because going from one vertex to the other just creates the sides. So obviously, if you have a triangle, you have one triangle. If we move up to a quadrilateral and we draw all the diagonals that's possible for one vertex, you end up with one diagonal. And that one diagonal splits it up into two triangles. So a quadrilateral can be constructed using two triangles. Now for a pentagon, if we draw all the possible diagonals from one vertex, we end up with two diagonals and three triangles. And in a hexagon, we end up with three diagonals and four triangles. So this shows you that every higher order polygon, higher than a triangle, can be divided into triangles. This is why we spend so much time on triangles in geometry, because everything bigger than a triangle, anything that's got more sides than a triangle, can be broken down into triangles. And then you can use all the things that we've learned about triangles to do things with that polygon. So the sum of the angle measures of all the triangles equals the sum of the angle measures of the polygon. That's the big takeaway here. So let's take a look at what that means. A triangle has three sides. We end up with one triangle in the triangle because there's no diagonals to split it up into more than one triangle. So the sum of the interior angles is going to be 1 times 180. So you end up with all the interior angles measuring 180 degrees. We've learned this already. It's the triangle sum theorem, that all the angles of a triangle, all the interior angles of a triangle equal 180. Now let's go to a quadrilateral. We have four sides. That can be split up into two triangles. We just showed that here. So 2 times 180 gives us 360. So all of the angles of a quadrilateral add up to 360. In a pentagon, we have 5 sides, 3 triangles. 3 times 180 gives us 540 degrees. So all the angles of a pentagon add up to 540. In a hexagon, we have 6 sides. That splits us up into 4 triangles. And so we end up with 720 degrees. So what about an n-gon? Let's generalize this. An n-gon has n sides. The number of triangles we end up with, well, you have 3 minus 2, which gives you 1. 4 minus 2 gives you 2. 5 minus 2 gives us 3. 6 minus 2 gives us 4. So n minus 2 triangles. An n-gon has n minus 2 triangles when you draw all the diagonals from one vertex. So we can generalize this as n minus 2 times 180 degrees. And that gives us the formula to find out what the sum of the interior angles measure in any polygon. So in each convex polygon, the number of triangles formed is 2 less than the number of sides in. So that gives us the polygon angle sum theorem, that n minus 2 times 180 gives us the sum of our angle measures. So let's find the sum of the interior angle measures for each of these polygons. So for a convex octagon, remember we're using convex so that everything happens on the interior, okay? So for a convex octagon, we start with n minus 2 times 180. The number of sides in an octagon is 8, so our n here is going to be 8. And 8 minus 2 gives us 6. 6 times 180 gives us 1080. So the sum of our angles in an octagon add up to 1080 degrees. For a convex heptagon, a heptagon has 7 sides. So here our n is going to be 7. 7 minus 2 gives us 5. 5 times 180 gives us 900. And for a 15-gon, this one's even easier because you know that in a 15-gon, n is obviously 15. So we're just going to put 15 in here. 15 minus 2 is 13. 13 times 180 gives us 2340. All right, moving on to example 2. Let's find the measure of each interior angle for each of these polygons. So for each angle, if it's a regular, we know that all the angles are going to be the same. For a regular nonagon, we're going to take n minus 2 times 180 to find out what the sum of the angles are. And if we want to find out what each angle is, we're going to divide that by the number of angles, which is going to be n. So for a nonagon, we have 9. So we have 9 minus 2 times 180, and we're going to divide that by 9 angles. And that's going to give us 140 degrees. For a regular decagon, that's going to be 10 sides, and it's also going to be 10 angles. And since it's regular, all 10 angles are going to be the same. So that gives us 144 degrees. And then finally, for a regular 16-gon, we have 16 minus 2 times 180 divided by the 16 angles, since all 16 angles are the same. You can only do this for regulars because we know all the angles are the same in a regular polygon. Okay? Now in example 3, let's find the measure of each interior angle of the given polygon. So we are going to use the information we know. First of all, we need to find out what all the angles add up to. So to do that, we know we have a quadrilateral, so that's going to be 4 minus 2 times 180 degrees. And that's going to give us 360. You have to do this first to find out what all the angles measure because it's different for every polygon. Now we know that all 4 of these angles are going to add up to 360. So we have C plus 3C plus C plus 3C equals 360. Okay? So if we add up all of our C's, we get 8C equals 360. And so C is going to be 45. So now that we have C is 45, we're going to find the measure of our angles. Well, we know that the measure of angle P is equal to the measure of angle R, which is C, which is 45 degrees. That's the easy one. The measure of angle Q equals the measure of angle S, which is 3C, which is 3 times 45, and that's going to give you 135 degrees. So if you add 135 and 135 and 45 and 45, that will come back around and give you 360. So we've talked about interior angles. Now let's talk about exterior angles. In polygons, an exterior angle has been measured at each vertex. Notice that in each case, the sum of the exterior angles measures is 360. Okay? So here we have a triangle, and we create exterior angles by extending each of the sides in the same direction. If we add up all these angles, you get 360. Well, then we take a pentagon and do the same. If we add up all these exterior angles, again, we end up with 360. So the polygon exterior angle sum theorem is even simpler than the interior angle sum theorem, because in a convex polygon, the sum of the exterior angles is going to be 360 degrees, no matter what type of polygon you have. So let's use that information to find the measure of each exterior angle of each of these polygons. So for a regular hexagon, you've got 360 degrees. You're going to simply divide it by the number of sides, which is 6. And that gives you 60 degrees. And let me just write this out for you just so you can see. We're going to divide it by the number of sides. In a hexagon, you have 6 sides, and so you end up with 60 degrees per exterior angle. For a regular 20gon, again, we have 360 divided by n. In this case, n is 20, and so that's going to give us 18 degrees for every exterior angle. We can do this for regulars, remember, because all the interior angles are the same, which means all your exterior angles are also going to be the same. 360 divided by n in a dodecagon, you have 12 sides, or 12 angles, and that gives us 30 degrees. So in example 5, we're going to find the value of the variable in the given figure. So here we're just looking for a. So to do that, we're going to add up all of our exterior angles, 7a plus 2a plus 3a plus 6a plus 2a, and all of those are going to add to give us 360. Well, when we add all of our a's together, you get 20a equals 360. And so a is going to be 18 degrees. All right, so that does it for this section. Coming up in the next section, we're going to start looking at specific types of quadrilaterals, and we're going to start with looking at parallelograms. So the next couple of sections, we are going to be focusing a little bit on quadrilaterals and the types of quadrilaterals we have.